You're sitting in the exam hall. The clock is ticking. You flip the page, and there it is. A 4-mark Cambridge IGCSE question on stretching springs, or maybe a complicated balancing beam experiment. You quickly scribble down what you think is a perfectly logical explanation. But flash forward to results day, and you've somehow missed the grade boundary. Why? Well, because simply knowing the formula, that's just not enough anymore. Look, in this explainer, we are plunging straight into the matrix of the Cambridge mark scheme. We're going to decode exactly how these examiners want you to answer questions on forces, Hooke's law, and moments. Because by the time we're done here, you won't just be plugging numbers into a calculator, you'll be literally engineering top-band answers.
When you walk into that exam, you're essentially standing in front of 3 doors. Door 1, that's relying entirely on your memory, just crossing your fingers and reciting textbook definitions word for word. Door 2 is guessing, kind of just throwing a bunch of vague explanations at the paper and hoping you accidentally hit the keywords the examiner is hunting for. Let me tell you right now, neither of those doors will protect your grade. The only safe path here is Door 3, the mark scheme framework. And spoiler alert, this is the exact step-by-step logic that actually survives the harsh reality of Cambridge grading. It's really not about what you know in your head, it's about exactly how you prove what you know on that paper.
Okay, let's dive into this and locate exactly where we are. We're looking at Section 3, Forces and Pressure. Now this right here, this is the ultimate battleground for high-mark practical and theory questions. We're talking forces and turning effects, center of gravity, more about moments, and stretching and compressing. The thing is, the examiner isn't just going to ask you to spit out a definition for these. Oh no. They're going to ask you to analyze raw data, design data tables from scratch, and plot graphs based on these exact syllabus points. And that is exactly where our framework comes into play.
Now you might be wondering, why does ordinary repetitive revision fail so many smart students in this specific section? Well, it all comes down to one really painful mistake: bleeding easy marks to vague explanations. You might understand perfectly well how a spring stretches, right? Or how a seesaw balances. But if your written answer lacks the correct scientific terminology, or if you make a careless graph axis error, or, and this is a big one, if you suggest a weak practical improvement like, oh, just do the experiment more carefully, instead of saying, take readings at eye level to avoid parallax error, boom. The examiner's red pen is going to strike. Knowing the physics is literally only step 1 of this game.
To stop bleeding those marks, you need a system, a reliable engine. This is our top-band 4-step framework, and it's designed to convert a basic, panicked exam response into a high-scoring masterpiece. Here's how it works. Step 1, state the concept. Ask yourself what physical law is actually at play here. Step 2, evidence or data. You must quote the numbers directly from the table or graph they gave you. Don't just wave at them, use them. Step 3, scientific reasoning. This is where you connect your data back to the concept using a specific equation or a logical step. And finally, Step 4, examiner wording. Lock the whole thing in with exam-safe phrasing. Use terms like directly proportional instead of a vague phrase like, it just goes up. Seriously, memorize this sequence. It's a lifesaver.
Let's move to and see how this builds when we apply it directly to a classic Hooke's law. Now, the baseline definition you absolutely must know is that extension is directly proportional to the applied load, provided the limit of proportionality has not been exceeded, right? And this relationship defines the spring constant K. But let's run this through our framework. First, the concept, Hooke's law. Next, the evidence. You have to correctly identify your variables from the apparatus they show you. Your independent variable is the load, the actual weight you're adding. Your dependent variable is the extension. And remember, extension is not just the new length of the spring. You have to physically subtract the original length. That's a massive trap people fall into.
And what happens if you ignore that data?
Say you just write a really nice general statement about springs, but you never actually reference the specific values the exam paper handed you. 0. That is exactly how many marks you get. Yep, 0 marks for conclusions that aren't supported by the provided data. In a practical investigation question, if they give you a table of forces and extensions, your written conclusion must explicitly reference those exact numbers to prove that proportional relationship. No numbers, no marks.
Now, what's really interesting about this slide is seeing that framework practically in action. Look at the flawed student error on the left. It says, the spring gets longer as you add weight. I mean, yeah, it's true, but it earns absolutely nothing. It's way too vague. Now contrast that with the improved top-band answer on the right. Extension is directly proportional to applied force, where the spring constant K equals F divided by X. Do you see the difference? It uses the correct terminology, it implies a clear mathematical relationship, and it completely prepares the ground for substituting your values. That is what the examiner wants to see.
All right, we are about to look at an even trickier topic.
In a moment, I'll show you the exact examiner clue that completely flips a measly 2-mark answer into a full 4-mark answer when we move from linear forces over to turning effects. But first, you really need to firmly grasp the framework we just discussed, because the traps are about to get a whole lot more subtle. Stick with me here, because missing this next step is exactly where most students lose their A-star.
Okay, let's escalate the stakes. Let's talk about moments and center of gravity. A moment is the turning effect of a force around a pivot. The equation, as you know, is force times the perpendicular distance from the pivot. Now, Cambridge loves, and I mean loves, to test this with practical investigations. They'll ask you how to find the center of gravity of some weird, irregular lamina, or how to balance a meter rule reliably. The secret key here? Safety and reliability. If the experiment involves hanging heavy weights off the edge of a bench, you absolutely need to mention safety precautions in your answer. Stuff like placing a soft pad underneath the weights just in case they fall. That's how you snag those practical marks.
But here is where the method marks just get completely destroyed. The common traps. Trap number 1, missing units. Listen, a moment is not just a floating number, it's a number with a real physical meaning. Trap 2, rounding too early in your multi-step calculations. Do not do this. Keep the full messy number in your calculator until the very end of the problem. And trap 3, wrong variables. Honestly, the most common error in moments is when a student multiplies the force by the total length of the beam rather than the perpendicular distance from the pivot to the force. Don't let them catch you on that.
All right, time for an interactive challenge. I want you to actually pause this explainer for a second. Imagine you're looking at a data table comparing force and distance on a balanced beam. Now, to maintain perfect balance, the product of those two, the force times the distance, should always be constant, right? So if you systematically multiply each force by its corresponding distance in that table, and the result of one specific pair suddenly spikes up or drops way down compared to all the others, can you spot what that means? Yep, that reading is your anomaly. This is exactly how you analyze data logically, directly addressing the evidence right in front of you instead of just guessing.
Notice the massive difference here. If your final calculated moment is like the one on the left, just the raw number 40 sitting there, you lose the final accuracy mark. Poof, gone. But the right side, that is what guarantees the grade boundary. It's the correctly substituted and rounded moment with nm, Newton meters, attached to it. Or if you used centimeters, NCM. You must explicitly show the examiner that you understand a moment is a combination of force and distance. The units are half the battle.
So the crucial point here is the number 3. In these calculation questions, there are typically 3 essential method marks up for grabs. One mark is just for stating the correct equation, like writing out m equals f times d. Your second mark is for actually showing the substituted values taken directly from the text or the diagram. And your third mark is for that final answer, complete with correct units and the right significant figures. Do not skip your steps in your head. Show you're working out on the page to secure all 3 of those marks, because even if you make a silly calculator error at the very end, you'll still get the first 2.
Before you even think about turning the page to the next exam question, I want you to run through this ultimate checklist. We've already talked about units and significant figures, but what if it's a graph in question about Hooke's law? You need to check your graph scale. Does your line of best fit occupy more than half the page? It better. Have you clearly circled any anomalies on the plot? And for the practical questions, have you discussed uncertainty? Like, did you mention using a set square to ensure the ruler is perfectly vertical when you're measuring the spring's extension? These are the little details that separate a B from an A star.
And this brilliantly illustrates our final challenge. Think about it. You now have the 4-step framework. You know the common traps for Hooke's law and moments. You know exactly how to secure those 3 method marks. But wait, you are still at a huge risk. What happens when you apply this whole framework perfectly, but you fundamentally misunderstand the command word right at the start of the question? I mean, if the examiner explicitly says evaluate and your answer just describes the situation, the entire framework collapses. You'll be hard capped at a much lower mark band no matter how good your physics is.
We opened door 3 today, giving you the ultimate framework for forces. But seriously, what good is a perfect framework if you are answering the wrong question entirely? To truly bulletproof your final grade, you have to decode those examiner command words. Are you ready to see how a single word can literally change your entire grade? Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations, and let's decode those command words together in our next explainer. I'll see you there.